This is Chapter 7, Estimating Parameters and Determining Sample Size. We are in Section 7.1, Estimating a Population Proportion. This section presents methods for using a sample proportion to make an inference about the value of a corresponding population proportion. First thing is give a star to point estimate. It's a single value used to estimate a population parameter. We use p hat or x bar. And a sample proportion p hat is the best point estimator of the population proportion p. It's unbiased. Next thing to give a star to is the confidence interval, or the interval estimator is a range or an interval of values used to estimate the true value of a population parameter. You use this all the time. You walk out of an exam and you feel pretty confident that you passed. You might say, oh, I feel confident that I got between an A and a C. And you have an interval of values that you're confident that's between. Next thing that we have is a confidence level, is the probability of 1 minus alpha, such as 0.95 or 95%, that the confidence interval actually does contain the population parameter, assuming that the estimation process is repeated a large number of times. Alpha is called the degree of confidence or the confidence coefficient. An example of the correct interpretation of a confidence interval: we are 95% confident that the interval from 0.405 to 0.495 actually does contain the true value of the population proportion p. So we don't know what that proportion p is, but we know that we're 95% confident that it's between 0.405 and 0.495. So there's an example below. It says a USA Today Gallup poll asked 1,006 adult Americans how much it would bother them to stay in a room on the 13th floor of a hotel. Interestingly, 13% said it would bother them. The margin of error was 3 percentage points with 95% confidence. Which of the following represents a reasonable interpretation of the survey results? For those not reasonable, explain the flaw. First thing is, it does say that we are 13%. 13% it would bother them to stay on the 13th floor. And we have another idea over here which says the margin of error is 3 percentage points. So that means 13% of people were bothered by staying on the 13th floor. And we have this margin of error, which means that's your plus and minus 3% points. So that means that it's actually between, subtracting 3 from 13 is 10%, and adding 3 to 13, it would be 16%. And again, that's written as percentages. It could be written as decimals also. So, first interpretation, there are 4 of these. Only one of them is correct. I'm going to go ahead and look at these, and I want you guys to figure out which ones are incorrect. So if it helps to pause the video and try to read those on your own. So most students usually say that B is wrong. So this one's not correct. And I'll verbally say the reason. You guys can always check on the scanned notes for the reasoning in writing that are posted on Canvas. So this is not correct, and the reason why is because it says that it's between 92% and 98% confidence. We don't say anything changes with your confidence level. Your confidence is 95%, and that does not change. So B is not correct. Another one that most students will say that is incorrect is D. And they say this is not correct because we don't know anything about, it says 13% of adults Americans would bother them, but we don't know within how much. What's our margin of error? We just don't have that information. So it's missing information in it. Or to say the interval that it's between. The other one that is incorrect is that C is incorrect. And this is saying in 95% of samples. it's not 95% of samples. That's our confidence level. So that's saying we were 95% confident that. So this is not correct. So I want you guys to take a moment and look at A, which is correct. So A says we are 95% confident that the proportion of adult Americans who would be bothered to stay in a room on the 13th floor is between 0.10 and 0.16. So a confidence level of 95% tells us that the process we're using should, in the long run, result in a confidence interval limits that contain the true population proportion 95% of the time. So on the second page it says, suppose that a random sample size n is obtained from a population which each interval either does or does not have a certain characteristic. Then we need to know how to calculate p hat. That's x divided by n, where x is individuals with a specific characteristic, and n is going to be your sample size. So there's an example here. It says, in a town of 500 households, 220 have a dog. The population proportion of dog owners in this town, expressed as a decimal, is. So we're going to take our 220 and divide by 500. And it does say to express it as a decimal, not as a fraction. So when you divide this out, we get 0.44. And it says a second survey of 500 households, especially if you went to a different area, would have a different proportion P. And really quick, we should give that P should have a hat on it. So put a hat on that P. So because P hat varies from sample to sample, it's a random variable and has a probability distribution. To get a sense of the shape, center, and spread of the sampling distribution, we can, I'll let you guys kind of read through those on your own. Next thing we have is a critical value, is a number on the borderline separating the sample statistic that are significantly high and significantly low. So again, depending on the cutoffs that we're going to be using, we're going to have significantly high, and then significantly low. And then again, anything in the middle is not significant. For example, a 95% level of confidence, or alpha equals 0.05, implies that 100 different confidence intervals are constructed, each based on a different sample from the same population. Then we would expect 95 of those intervals to include the parameter and 5 to not include the parameter. 95% of the time the parameter will be included in the interval. And you guys can see there's total area under the curve is 1, or as a percent, it would be 1%. And then 95 means 5% is left over, but to split it between those two tails, we have to divide it by 2. So alpha up here was the 0.05. So to figure this out, you got to do alpha divided by 2, which is 2.5%, or 0.025. Likewise, the same here, alpha divided by 2. 95% confidence does not tell us there's 95% probability that the parameter is between the lower and the upper bounds. So we have on here, we have our critical values. And I want you guys to notice it does say Z alpha over 2 over here. And we have our alpha values. And to figure out alpha, this is going to be 1 minus our confidence level. So alpha equals 1 minus confidence level. So if you're 95% confident, it'd be 1 minus 0.95. These are the most used ones. So I usually would have this given to students on an exam. It wouldn't be something that they have to have memorized. The example at the bottom of the page says calculate the critical value for a 98% confidence level around 3 decimal places. So not always do we always have those values that are up there, especially on My Open Math. So you guys want to make sure that you have this example, so if it ever asks for 98% confidence. That means your confidence is always in the middle, so we have 0.98. And so 1 minus 0.98 is 0.02. And then splitting that into those two tails, so dividing it by 2, we have 0.01 in each of these tails. And again, your total area, oops, that's 1, under a curve should equal 1. And so when you have this, when we set this up, we have a standard normal curve. And with the standard normal curve, we have the mean is 0 and the standard deviation is 1. So in order to calculate our Z1, and we'll go over and label that on our graph since we do have two values that we need to find. So we'll call this one Z1 and this one Z2. Again, if you want to put the mean of 0 in the middle, realize that one of those values will be positive and the other one will be negative. We've done this before because of the symmetry with the bell-shaped curve. The numbers will be the same, but one will be positive and one will be negative. So in order to calculate Z1, we'll use inverse norm. It's the area to the left, and for the first one, it's 0.01, comma, the mean, which is 0, comma, the standard deviation, which is 1. To calculate Z2, we would use inverse norm. The area to the left is 0.98 plus the 0.01, which is going to be 0.99. The mean is 0, standard deviation 1. Calculating these, the first one you're going to get negative 2.326. And for the second one, you're going to get 2.326.